Okay, welcome back to Real Analysis. We have been, up until now, spending some time constructing the real numbers. And today what I'd like to do is to talk about some further extensions of real numbers. In particular, we want to spend a little bit of time on complex numbers. And then in the second half of the lecture, we'll begin talking about the principle of induction, which is a very important proof technique. And as you'll see, it has its foundations in a particular axiom for the natural numbers. Okay, so let's begin. So last time we mentioned that the real numbers were they could be defined very naturally in terms of cuts. These are Dedekind cuts. The construction basically involves constructing real numbers from the rational numbers. But we also saw that the real numbers were characterized by some properties, right? So that real numbers are basically the only complete ordered field with a particular property, the least upper bound property. Okay. So today I want to talk about a few extensions which are often convenient, that are not necessarily going to enjoy all the nice properties of real numbers, but they're sometimes useful. So the first thing I want to mention is something called the extended reals. And this is more a convenience than anything. I will define the extended reals, and sometimes it's signified with R with a bar over the top. Remember, this colon equals, I'm going to use to mean it as a definition. I'm going to define this to be the reals together with a couple of extra points. Okay? So as an abstract set, it's the real numbers together with two extra points, which I will denote by minus infinity and plus infinity. Okay? You can't stop me from making a definition like this. Okay? Now, of course, it would be a rather pointless definition if I didn't also tell you how these creatures work with the structure that's already on R, the one we're used to associating with it. So as a set, it's this creature, but we actually can order this set. So R already has an order. The usual one on R, and then together with telling me how minus infinity and plus infinity behave. So where do you think I'm going to place these things in the order that's on R? Yeah, at the very ends. How about for all x in R, I'll just demand that x be whatever it is, if it's one of the real numbers, less than plus infinity and bigger than minus infinity. Okay? The usual order on the reals, but then together with this. Okay? And now you might say, well, what about an arithmetic? Okay? Is there can I extend the arithmetic on the reals to the extended reals? And the answer is, yeah, you can try. And so here's at least a partial attempt at an arithmetic. Maybe we'll say that there's the usual addition on real numbers, but if you ask me to add a real number to positive infinity, then I should get what? Yeah, positive infinity, right? And how about if I add minus infinity to x, I should get what? Minus infinity, okay. Certainly can't stop me from making that definition. Everything, is okay for the most part there. And you can make a few more other definitions as you like, right? For instance, if x is bigger than 0, we'll define x times positive infinity to be positive infinity. And if x is less than 0, x times positive infinity be negative infinity, etc., etc. Okay, you can basically do things in the natural way. Yes, Jenny, question. Oh, yes, very good question. Yeah, and there's a reason that you can get so far, but you can't finish all these definitions without running into some problems. And so there are a few things you leave undefined. I guess there are a few things you could do. You could still do. I mean, there are a few more things I didn't mention. You could define x divided by plus infinity to be 0. Okay. But there are some things that you can't, so etc. There's some things that you'll have problems with. So for instance, 0 times plus infinity. Well, you can see you might begin to run into problems if you make this kind of definition. 0 times plus infinity should be what? It's not well defined. Okay. Or another thing you might have a problem with is how about plus infinity plus minus infinity? What should that be defined as? No good way of doing that. Okay, so this thing is, the upshot is it's not a field. Okay, it's a set with some structure, but it's not a field. Okay, but why do we care about thinking about the extended reals? Well, it's convenient sometimes, right? So why care? It's convenient. One thing that it ensures, so for example, if you tell me to take the supremum of a set, well, the set, in this case here, every set is going to be bounded, right? It's going to be bounded by plus infinity. Every set will have a supremum, okay? So every set in our say subset of R bar, the extended reals, has a supremum, or if you like, an infimum as well. Now, of course, possibly the supremum could be plus positive infinity. That's just another way of saying the set is unbounded if its supremum is positive infinity. Okay. If it's bounded, then of course it's going to have a supremum where? In the real numbers, the usual reals. Okay? But it's convenient. So sometimes you will see this kind of notation, right? An unbounded set, you'll see the supremum of a set might be plus infinity. Okay. So that's the main reason we care about the extended reals. Okay, what are some other structures that are built around the real numbers, having the real numbers as a foundation? Well, here's another one. How about Euclidean space, R to the K? So the way I think about R to the K is I'll think of it as ordered K tuples. So that's basically a collection, a multiple collection, it's a tuple of K things, right? So x1, x2 through xk. It's an ordered collection. So the order matters. So 1, 2, 3, 4, 5, 6, blah, 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 k is different than 2, 1, blah, 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 k, right? And I'm just demanding that each of these creatures, each of the xi's are in R. Okay? So it's collections of real numbers. Okay. Once again, this is a set, and it becomes more interesting when you give it a structure. Okay, so what's one of the first things you might do to give it a structure? Order. Well, you might try, okay. And certainly you could give it, there's nothing stopping you from giving it the lexicographic order, right? Where you dictionary order, if you like, comparing things, first the first thing, then the second thing, etc. Okay, but that, we don't often give it that kind of structure because it doesn't happen to be so useful for many of our purposes, right? Okay. What's another structure you might try to give this set, Willie? Yeah, some kind of arithmetic. So the first thing you might think of is addition. Perhaps you want to add two k-tuples. Maybe the one k-tuple is x1 through xk, and I'll ask you to add that to y1 through yk. And what's a natural way to define this addition so that what you get back is also another k-tuple? Yeah, just add element-wise. Everybody's done this before. If you're in this class, you've gotten here because you have done something like this before. You think of this sometimes as a vector. Okay? There's a reason for it, because what we're about to do is define a vector space structure. Now, sometimes we denote this by a little symbol that allows us to refer to the thing without writing out all the k pieces. Okay? So this is addition, element-wise. Question. What's another thing you might try to define for a set like this with an addition? Harris? Okay, well, you might try to define some kind of multiplication, okay? And I'll just tell you in advance that the obvious way to multiply doesn't lead to anything that's very nice, right? You might, for instance, multiply two vectors and get another vector by multiplying coordinate-wise. It's the first thing you might think of, right? Certainly, you can check if you wanted it to be to have some nice properties, you can check that that is certainly closed under multiplication, produces another vector. It's commutative and associative. In fact, it has an identity element consisting of all ones, right? But no notion of inverse, right? So that element-wise multiplication, not so nice. It doesn't turn this thing into a field. Okay? Okay, so we generally don't try to endow it with a field structure. But it does have another kind of multiplication, which gives it what's called a vector space structure, and that's scalar multiplication. And what I'll have you notice about scalar multiplication is that when you multiply a vector by a scalar, which is basically an element from the real numbers, so this is nr. We sometimes call this a scalar. It just means something nr. Well, okay, you do the natural thing, which is you basically take everything and multiply it by this scalar alpha. Okay? Notice, this is not a multiplication that takes in two vectors and spits out another vector. It takes in a vector and a scalar and spits out a vector. Okay? Bonnie? There isn't yeah, so the question, so if you have a bunch of ones here, if one is behaving like an identity, which it is, then you might ask yourself, is there some way, if this were a times, to multiply, you give me a vector, multiply it by something to get a bunch of ones. You're going to see you run into problems as soon as any of the coordinates are non-zero. Some of the coordinates are 0, but not all of them. Okay? So if you want it to be a field, there should be a single element that's not invertible, that doesn't have a multiplicative inverse, right? And that should be the additive identity. The additive identity here is the vector consisting of all zeros. So with the obvious multiplication, you won't have every element There'll be some non-zero elements that are not invertible. Okay. Nice question. Yes?
So, despite the other problems with coordinate-wise multiplication, would that preserve dictionary order or lexicographical order?
Oh, interesting. I haven't thought about that. That's an excellent question. Haven't thought about that. But what you're making an argument for is that that particular multiplication might have some natural pairing with the lexicographic order, right? I haven't thought about that. It's something that'd be great for you to think about and see if something interesting can be said. Okay. Okay. Yes. Question, Paul. Equality means basically, yeah, so I didn't say this, but two vectors are equal if every element is equal. Are you suggesting a different notion of equality?
No, I was just wondering if there was one, actually.
Yeah, we'll say that every element is equal. Okay. Now, of course, you might want to consider something that's a little more of an equivalence, a little more relaxed, right? You might say if you had different equivalence relation, you might let some of the things be equivalent to other things if certain things are true, but not something we normally do with this space. Okay. Okay, lots of excellent questions. So what do we have here? We have an addition, we have a scalar multiplication, and you can see that this scalar multiplication, even though it's not a full-fledged multiplication of two vectors, it does satisfy, does enjoy a lot of the properties that we liked when we were talking about fields. So in particular, it happens to be associative, distributive. With addition, it satisfies distributive property. It's commutative, associative, distributive, etc. Lots of nice properties. And so it turns all these laws hold. So it turns RK into what's called a vector space. And this is something you'd study more in an abstract algebra course. Okay. Quick save there. Okay, very good. What else? Well, RK also has some additional structure. It has what's called an inner product. And again, there's some overlap with your algebra course. In a multivariable calculus class, you sometimes say the word dot product instead. In an advanced linear algebra course, you might say inner product. And this is a multiplication of vectors, a product of vectors, that doesn't spit out another vector, it spits out a scalar. Yes, so here, x dot y is defined to be the, oh, interesting, element-wise product, but then you add everything together. Okay, and this symbol, sigma, stands for sum. Okay, it's a Greek letter sigma. And it basically means take this index sub I, each of the i's here run from 1 through n, add them all up. Okay, so this is maybe a new symbol for some people. It's a summation. It means add things up where you run through each instance 1 through n. Or excuse me, k in this case, because I used, I'm thinking of this in RK. Okay? Right. Inner product. Okay. What does this do for us? Well, it's a notion that actually has some important geometric intuition, which you've studied some already in multivariable calculus or linear algebra. One of the first things that you can do with an inner product is define a norm, which is a notion of length. In linear algebra, you might, for instance, call this the length or the magnitude or the absolute value, symbol sometimes used. And you define this to be the inner product of x with itself, take its square root. Okay. Really? Why? Why in the world would I think about doing that? First of all, can I even take the square root here? Well, what happens when you multiply, take the dot product of x with itself? Each of these entries is a square and therefore not negative, right? It might be 0, okay? In fact, the only time it is 0 is if everything's 0. So the only 0 has, the vector 0 is norm 0. But the point is the square roots are possible, and then you have a length. And this length corresponds with the geometric notion of the Euclidean length. You know, so if you have a point here, x1, x2, then this length is going to be the norm of x, the length of the hypotenuse. There are lots of other notions of length. And of course, when we start talking about the word metric space, we will be, in fact, working intimately with notions of length like, but not necessarily the same as this one. Okay, very good. I think that's all I want to say right now about the Euclidean spaces, but we may return to them soon. Now, it turns out that there's another way to, if you like, extend the reals in such a way that you, in fact, do get a field. Okay, this creature's not a field. We don't have a natural notion of product that has the right kind of notion of inverses. But you can define an extension of R. In fact, the set itself will look like R2, but it will have a field structure. So let me just mention that these are called the complex. This is the complex number field. And the point is here that R2 can be given a field structure. It's just not the one you might first think of. And what do you mean by that? Well, what I mean is you give me ordered pairs, and I know how to add them. That will be just like I expect. In fact, I'll put the comma here. But the multiplication, well, that's a little different than you might expect. We're going to, rather than straight multiply elements, we're going to twist our construction in a most interesting way. In particular, I'll let the first element be AC minus BD. And then the second element will be AD plus BC. Interesting. That's a very funny notion of multiplication. But it does indeed yield a new new ordered pair, right? Okay. And so now the question is, why is this a field structure? I have a multiplication and an addition. And of course, the point is this is a field because it'll satisfy all the axioms. You just have to tell me what the 0 and the 1 are. What is the additive and multiplicative identity? Here, what plays the role of 0? the 0 of the field. This is when you say 0 of the field, you mean the additive identity. And the 1. Okay, now what do I mean by that? I just mean the additive identity, right? We're not searching for the 1, right? This is the additive identity, right? What is the 1? The multiplicative identity, right? Yeah, not additive, multiplicative identity. Well, you can check that the multiplicative identity is actually pretty simple too. It's just 1, 0. And I'll let you check these things. But convince yourself of this. If I put, if I let C be 1 and D be 0, then these two terms drop out, and you get A comma B, right? There's a little more work to verify that there are inverses, but this is all rather nice. Okay. Now, the other thing that's great about this is that this complex number field actually does extend the reals in a natural way. So first of all, let's call this field C, which is, so it's basically this. It's a set. As a set, it's equivalent to R2 with plus and times as above. Okay, but the point is, with this additional structure, we'll think of this as the complex numbers. And here's a point we want to make. C extends R in a very natural way, in much the same way that R extends Q, right? And Q extends Z. There is a subfield of C that behaves just like R. Really? What is it? Yeah, let's look at all ordered pairs A comma 0 where A is in R. This, if you just make all the B's and D's here 0, then in fact you just get the usual addition of the first coordinate, and in the second coordinate, here this is 0, and this thing just becomes the multiplication, right? So in fact, this set behaves, it's a subfield, it behaves like R. So it's a subfield. Another way to say this is it's a subfield isomorphic to R. If you know that word from algebra, fine. If not, all it means is it behaves just like R, your usual arithmetic on R. Oh, that's great. It's beautiful. So because of this, and because of the following property, so here's another thing to notice. If I look at the element 0, 1, it actually, you can check that 0, 1 times 0, 1 under this arithmetic is just, well, let's see, all the A's and C's are 0, and that makes this 0, and that makes this minus 1 times 1, which is minus 1, 0. So something very special happened here. The thing that's this element which is 0 in the first coordinates produce something which is 0 in the second coordinate. Okay, and so if these are the real numbers, something that isn't real, when you multiplied by itself, gave something that was a negative real. Right? So we're beginning to see that this field has a very interesting property. If I call this creature I, you can't stop me from doing that, then what I see is that I squared is, if you like, minus 1. If I think about this as a real number. As a special subfield here under the correspondence where I think about it as the real number. Okay. Oh, that's beautiful. Okay. And so we normally write, because of this, we often write a plus bi for the element a comma b. This is the more usual way of writing a comma b. We'll write it as a plus bi. Because after all, isn't it 1, 0 plus 0 plus, isn't it a0 plus b times 0, 1? Okay. All right. Great. And if we do that, we still do the following. We still think about a complex number as an ordered pair. It's just that it has a part here that in the first coordinate behaves like the real numbers. So we think of this as the real part. And it has another part which, because it's not the real part, we think of it as the imaginary part. And this term, by the way, arose because in a very derogatory fashion, right? You know, it basically, I can't remember which mathematician it was, but the mathematician who first coined this term basically said, oh, you know, imaginary, that part's imaginary, as if it really didn't have useful purpose, although we see now these days that it does serve useful purpose, and there's nothing imaginary about it. It's all part of some construction. Okay? Okay. Good. Well, there's also several geometric notions associated with this creature. So if z is a plus bi, we'll define z bar to be a minus bi. So the imaginary part gets negated, and this is called the conjugate of z. Okay. And I should mention then, if you write this as a plus bi, a is called the real part of z, sometimes denoted rez, and b is denoted mz, which stands for the imaginary part of z. The real and imaginary part of z is what? They're both real numbers, aren't they? Okay? The imaginary part refers to the coefficient of I. Okay, great. So just to test our understanding here, if you take the conjugate of z, what do you get? Z, because the imaginary part of z conjugate is what? It's minus b. Okay, so you negate that and you get back b. So the conjugate lives down here. If this is z, this is z bar. It's down here, just reflection around the real axis. Okay, great. Lots of things here you can check about the complex numbers. And I'll just let you check these things. It's very easy. But conjugation plays nice with addition and multiplication. So it's a very natural operation. So if I take the conjugate of z plus w, that's just the same thing as conjugating first and then adding the numbers. If I take the product and conjugate, that's the same as, believe it or not, taking the conjugates and multiplying. Again, you can check all these things very easily with these definitions. Right? Okay, so conjugation plays nice. A few other things you might do. Oh, by the way, I put periods here because this is a complete thought, right? This equals this, period. Okay. If I want to pick off the real part, you can add the conjugates to itself to pick off the real part. This gives twice the real part of z. And what if I want the imaginary part? Can I define that in terms of conjugation? Yeah, how about z minus z bar? And that gives twice I times the imaginary part of z. Okay. But perhaps the most useful property of conjugation is that when you multiply something by its conjugate, what do you get? What happens if you multiply a plus bi times a minus bi? You get, it's the difference of squares, a squared minus bi squared. But bi squared is minus b squared, so that's just a squared plus b squared. Oh, really? Nice. The thing to notice about this is that this is always real. It's a real number. And it's always bigger than or equal to 0. And in fact, if you think about this in this particular picture, if you think about one side here as A, and the other side as B. Oh. Not bad. Then, what do you notice about the hypotenuse? It's the square root of this creature, right? So, in fact, we will define the length of z, the absolute value of z, we'll say, that's what we usually say for this, or the length. The magnitude of a complex number is just going to be z dot z bar to the 1/2. Okay? Everybody with me? Oh, hey, that's kind of nifty. In fact, this length corresponds with the geometric notion of length if you just thought about the complex numbers as the real numbers, right? The R2, the real plane. Okay, so it coincides. It's the same as the length in R2. Okay, and what you see is I can find the length squared just by multiplying z times z conjugate. Okay, so in physics, this property is used a lot, right? If you want to find the magnitude, the amplitude of some, whatever it is, complex waveform, right? You can multiply something by its conjugate, right? Okay. Oh, okay. This also suggests something. It suggests that if I wanted to define a complex space that is just like Rk, except I do c to the k, I could also define a collection of complex numbers, right, whose dimension is going to be twice that of the real version, if I thought about this as a vector space over R. But what does it mean? I could also define an inner product. And the inner product on CK, well, it should look something like this, except I might do something slightly different, just to be consistent with what we see over there. What would I do? Conjugate one of them, okay? So I'm just going to mention that it suggests in CK, which is basically collections of Z1 through ZK, Zi in C, the inner product. What inner product? Okay, well, I'm going to do the following. I'm going to, let's give the inner product a special symbol. In physics or quantum mechanics, you often use brackets. I know some of you are physics majors here. And we use the same notation. The bracket is an inner product, and I might take a vector. Now, here, the x and y are vectors of complex numbers. And then I will define, and this isn't in your book, by the way, I'm just telling you because I think you'll find it interesting. This inner product is what? Well, it'll be a sum of all the pieces xi, yi, I goes from 1 to k, but I'm going to conjugate one of them, the right one, okay, the one that's in the right argument. Okay, so this is a notion of inner product that you'll have on a complex space. Okay, and if I want, then I could talk about length in the natural way. When you take the inner product of something with itself, guess what? You get something positive, and that's because z dot z bar is going to be bigger than or equal to 0, right? So you get something non-negative. Okay. That's the reason for this. Okay. All right. Very good. We'll come back to this in a little bit because you'll see it'd be important for something we're about to do. But returning back to complex numbers, just one of them. If you have this length, there's lots of things you could verify about it. So let's do that here. And I'll either let you verify it. A lot of these things are very easy to show. So the property, so some properties you can show about this length. Sorry, let me box this because it's rather important. Clearly, the length is bigger than or equal to 0. What can I say about the length of the conjugate? Same thing, a squared plus b squared if it's a plus bi. Good. Okay. What can I say about the length of the length of a product? Yeah, and if the world is a just world, you might hope that this is the product of the lengths. Is it? Take a guess. How people say yes? How people say no? Yes, it is. Okay, but it's not altogether obvious. So the main ingredient in showing this is this rather remarkable number theory fact, okay, which says the following. So it's based on this rather remarkable fact in and of itself. Namely, if I take AC minus BD, square it, and add AD plus BC and square it, that turns out to be, just do the arithmetic, turns out to be the product of a squared plus b squared and c squared plus d squared. Okay, that's rather remarkable. And this, if you're a number theorist, is an interesting identity because what it's saying is if you take the sum of two squares and something else that's the sum of two squares and you take their product, guess what? You get something that's the sum of two squares. Okay, if these were integers. Okay. To an analyst, well, I don't care about integers, right? These are all just whatever they are, complex numbers, real numbers in this case, right? True. Oh, nice. Okay, so how does taking lengths play, does it play nice with the arithmetic? Well, for multiplication, it does. Okay. Okay. What about addition? I should mention one more fact before we do that. The real part of z should be obvious that this is smaller than the length of z, just because it is the a, and you're comparing it. It's the side length compared to the hypotenuse. Right? Okay, let's see. Comma, 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 chameleon. No, sorry. And one more fact. How about z plus w? How's its length compare to length of z and the length of w? Yeah, enough of you have seen this. It's not the sum of the lengths, but it's smaller, less than or equal to the sum of the lengths. And this has a special name. It's a version of something we'll see later as called the triangle inequality. It's a version of the triangle inequality. And the reason it's a version of the triangle inequality, or the reason we call it that, is you could imagine these creatures, z as being a vector measured from the origin, and w being a vector also measured from the origin, but if I displace it to the endpoint of z, then this particular length, this dotted length here, that's the vector z plus w. And so the triangle part comes from noticing that one of the lengths, the z plus w length, it can't be longer than the sum of these two lengths, but it might be shorter because there's a triangle here. Okay? Okay, how do we show this? This isn't altogether obvious either. Why does the triangle inequality hold? We can do this. Well, let's just begin. I want the length of z plus w. I don't have a good way of dealing with the length, but I do have a good way of dealing with the length squared. Right? Length squared is z dot z bar. In this case, the length squared is, help me, so this is one of those proofs that once you see the thing to start with is this, then it's easy enough. This is z plus w times what? Z bar plus w bar. It's the conjugate of the other thing, right? Oh, but what's this? I can multiply this out. Anybody can. This is z dot z bar. Yes? Oh, cool. Help me. Z dot z bar plus z dot what? W bar plus w dot z bar plus w dot w bar. Oh, okay. But wait, what's this? That's z, the length squared of z. What's this? That's the length w squared, right? And what's this stuff? Well, check this out. Look, this is just the conjugate of this, right? And if I add two conjugates, what do I get? The real part of one of them, or the other, either one, right? Twice the real part. Oh, but wait, what's that? That's twice the real part of ZW, right? Oh, really? But wait, what's twice the real part of something? Now, what did I really want? What do I want out of this calculation if I want to show z plus w length is less than the sum of the two, less than or equal to the sum of the two lengths? Yeah, I'm kind of wanting to show that it would be enough to show that the square of this is less than the square of that. Do I see something like the square of that right-hand side here? Yeah, it would be nice, except I don't have 2 times the length of z, length of w here, do I? Do I have something close? What's the relationship between the real part of zw bar and the length, the product of the lengths of z and w? It's less than or equal to. right? It's one part of the hypotenuse. So this is the only place there's an inequality is right here. Is this length less than the length of z squared plus the length of, okay, twice. The real part is bounded by the absolute value. The absolute value of zw bar is the absolute value of z times the absolute value of w bar, which is the same as the absolute value of w. Yes? Plus w squared. Yes? So in fact, this part is just the length of zw squared. Okay? Everybody should see this proof at least once in their life. Not bad, right? It's kind of a nice argument. And this is enough to show this yields the desired inequality. So by ending a proof with this statement, I'm basically saying, hey, reader, look at what I just did and convince yourself it shows what I was trying to show. Right? Okay. Yes. Okay, very good. So what do we have here? We have that this creature, this length, plays nice, for the most part, with the arithmetic structure, except we have a triangle inequality in a place where you might have hoped there would be an equality. Yeah. Excellent question. The question was, would this be acceptable for a homework? And so I guess I would say what I said earlier about who your audience is. Your audience is somebody who's 2 weeks behind you. Okay, so maybe at the beginning of the class, you might want to help the reader a little bit. As we move further through the class, there would be some things you'll just expect the reader to follow, right? Yeah, so the answer will depend on basically who your audience is. Okay, so you're supposed to think of your audience as people who are 2 weeks behind you in the class. Okay, excellent. Perhaps the final thing that at least for now I want to say about the complex numbers. It's related to complex numbers, but it's also related to Euclidean space or complex vector space is a very famous inequality. It's perhaps one of the most important inequalities in all of analysis. It's known as the Cauchy-Schwarz inequality. It says the following. It says if you have A1 through AN, and these could be, often you think of them as real numbers, but they could be complex numbers. So imagine A1 through AN and B1 through BN. Suppose these are complex numbers. Certainly real numbers would still work. Then the following rather amazing inequality holds. It's not obvious when you write this down why it's so amazing, but we'll say why in a second. It says if you take, this is the way we'll write it first, the sum of AI, BI, and let's conjugate one of them. Now, if you're just dealing with real numbers, the conjugate of something is itself, right? So if you're dealing with real numbers, you can forget the bars. If I take the sum of the AI BI's, which you should recognize as something, what is it? It's the inner product. Whether you're dealing with real or complex vectors, think of these as a tuple of things, that this particular length, this is an inner product, it's basically the length of the inner product squared. Okay, this is going to be less than or equal to another corresponding creature, which is the sum of the AIs squared, times the sum of the BIs squared in absolute value, in their length. And again, if this were real numbers, you wouldn't have to take these lengths, because the square of this would you could just take the squares. You could ignore the absolute values here. And this is a product. Okay, what's so great about this inequality? Well, really what it's saying is the following. If you want to think about this as vectors, it's basically saying, in RK, it's saying v dot w in length is less than or equal to, when you take the dot product, it's less than or equal to the length of v times the length of w. How has this come from this? Take the square root of both sides, okay? Because this v dot v, or v dot w, is just going to be, if I want to take its length, that's exactly what this is, right? V dot w in length. Okay. Oh, nice. Yeah, in the complex, if I want to write this as if I were a physicist working on inner product spaces, I would just write it like this. This particular v comma w is less than or equal to, maybe the best way to write this is, this is the length of v, I could write it like this if I want, and then maybe I should square something here and take the length. Yeah, so v dot w, so this is going to correspond to the inner product. This is going to be the length, and this creature is going to be ai dot ai bar. Yeah, this is fine. This length is going to be this less than this times this. Okay, and these are real numbers, and they're bigger than 0, greater than or equal to 0. Okay. Am I missing something?
Just in the RK case, do we need to square the length?
Do I need to square something?
Oh, no.
No, I don't. Yeah, because yes, maybe. Let's see. This is the now I'm just. This is a length, and this is the absolute value of the dot product, and the dot product here is this creature. Do I need a square? Okay, now I'm. Yes, thank you. Okay, good. Sorry, I'm just getting a little confused by my own attempts to write this in a different way. Yes, right. If this had been a v dot v, then there would be a square involved. Right. But I took the square root of both sides. Okay. Cauchy-Schwarz. Why do we care so much about Cauchy-Schwarz? Well, for one reason, this is an inequality that you often encounter in multivariable calculus, right? When you think about v dot w as being the length of that as being the length of this times the sine of the angle in between, then you see that this particular inequality is true. In the complex vector case, this actually arises, it's actually the basis in physics of the Heisenberg uncertainty principle. Okay? And basically the Heisenberg uncertainty principle says something about That's something in physics, right? About position and momentum, right? They can't both be determined with very much precision, and it's based on the Cauchy-Schwarz inequality. Okay, so let's prove this. What can I say about the proof? I'm going to do a slightly different proof than that in the book. Actually, if you're good, I might do two proofs. But I'll give one that's equivalent to one in the book, but maybe easier now that I've made this definition to digest. So let's think about vectors in Cn. Okay, so let's let, instead of writing, I guess here I'm going to use the A's and the B's. I'm going to let A and B be elements of Cn. Okay, so they're vectors consisting of the AI's and the BI's. Okay. So the first thing that I want you to notice is it's very clear that the 0 is less than or equal to the following quantity. A minus YB in length squared. Now, I haven't told you what y is yet, have I? But it doesn't matter. Whatever this vector is, its length squared is bigger than or equal to 0, yes? And I'm going to pick y later on. Okay, I'm going to be that'll be my choice, right? And I'm going to do so in a nice way. Okay. Okay, here we go. What do I do with this? Oh, well, this is easy enough to write as the inner product of A minus YB. And if you don't mind, I'm going to stop running the vector symbols for now, because it just makes this a lot more to write. It's the inner product of A minus YB with itself. Okay. Oh, okay, but what's that? Well, the inner product, I mean, it basically, everything here is linear. This is a bilinear form in each of these entries. Everything just expands in the natural way if you just look at this definition. So if I want, I can rewrite this as the following. This is A comma A minus Y bar A comma B minus Y B comma A plus Y absolute value Y squared B comma B. How did I do that? If you like, I would put the intermediate step in. This is just, here if it helps, this is just the sum of A minus YB times A minus YB bar, everything barred. Sorry, these are vectors, right? So these are all the sums of the coefficients. These are the i's. Okay, I'll let you carry out the rest, but this is where it comes from. You can rewrite it like this. Okay, great. But what does this mean? Well, here's where I'm going to just choose y appropriately. Let's just let y, if you don't mind, be A comma B over B comma B. You can't stop me from making that choice. So if I make that choice and do that right here, what do I get? Well, I get basically something that's equivalent to A comma A minus, now when you put all this stuff in, you'll see lots of things just combine. Okay, so here we have AB over BB, and there's a B, so there's an AB squared over BB squared, and there's a BB here, right? Some cancellation. Here you have AB on top and BB on bottom, and there's a BA on top, and these things, when you flip, is just a conjugate. Same thing here. And basically what happens at the end is you get the length of AB over BB. Now, this creature is bigger than 0. But that's just the same as saying that if I multiply this whole thing by BB, I get AA times BB minus this thing. I think I've lost a square here. This thing should be a school. AA, BB. I think I've lost a square here. When you multiply through by BBAA, you get exactly what you want. Yields desired inequality after multiplying by BB. Now, I've just said this in a way that's equivalent to what's in the book, although the book doesn't use this language, but perhaps it's easier to see the structure of the argument in this way. The book, if you want, the book actually writes this creature as big C and this creature as big B. So if you want to see how the book does it, let's let Y be big C over big B. That's makes this proof equivalent to that in the book. Okay, Cauchy-Schwarz. It's going to come up a few times in this course, but it's good to know. Okay, and one of your homeworks asks you to think a little bit about the Cauchy-Schwarz inequality. How many people here are actually taking, or physicists are taking physics, quantum mechanics? Quantum mechanics, okay. You probably learned about Bras and Ketz. Or you're going to learn about Bras and Ketz? Okay. Well, Bras and Ketz are, the reason they're named such is because this is a bracket, right? It's a bracket. Okay, and so you deal with a lot of the linearity properties of the bracket in physics. Okay, great. Good. Any questions about complex numbers or anything we've done so far? Good. That is probably a good place to stop, because I did want to start talking about induction, but that's a whole nother subject, and it's something that would be better to wait till next time. So we will see you next time, and I'm not sure, Ryan, if there's. So we'll end the video part of this lecture now, and Ryan.